Hi, and welcome to 3.5a Horizontal Projectile Motion. In this lesson, students will be able to describe the motion of a horizontally fired projectile. So, what does the path of a projectile look like? Draw your answer and then compare with a table partner. A projectile is basically anything that's think of a ball being thrown. So let's say you have a person here and they're going to throw this ball somewhere. The initial velocity is going to point this way, but then what happens after that? I don't know. All right, think about your answer, and then we'll draw it together. So pause the video and draw the path of what that projectile would look like. What do you think? Okay, time to draw it. Let's add some vectors together. I want you to get 3 different color pens. Now this could be, you could use a pencil as one of the colors too. So maybe a pen, a pencil, and one different colored pen. So this is a classic thing I like to do, and I'm going to start by drawing the cliff from which we will throw our projectile. And our projectile is just going to be a ball, okay? So the ball's initial velocity is all going to be in the horizontal direction. Let's say somebody kicks it straight this way. But instead of that color, I'm going to use, we'll use blue for the horizontal stuff. So the initial velocity looks like this. Okay, where is that ball going to go? Well, in the y direction, let's start by looking at the y direction. If you were like standing on the side over here and looking at the path of this ball, if you didn't have any depth perception and you were looking at the ball here, then the ball would appear to start here and then drop straight down. So in the y direction, it's just like what we've been doing in the past, where the initial velocity in the y direction is 0. Even though there's a horizontal velocity here, that's all horizontal. The vertical velocity, it's not being kicked up or down at all. So the initial vertical velocity is 0, and then it speeds up because it's accelerating. So we'll draw that by drawing a small vector here. That's the vertical velocity. We could call that v sub y, and we'll call this vi x. And what happens to this is the velocity vector. What happens to this velocity vector is that it gets longer and longer. Okay, it gets faster and faster. I'll even draw this a little bit longer. So on your page, I want you to use a color for your vertical velocity vector. And so do that. Make a small arrow and then larger and then larger. So the question is, why does the velocity speed up? It's speeding up because gravity is causing you to accelerate. That's why your velocity is changing. So you have the planet over here, and it's accelerating towards the planet. If you think of the x side of things, is there another planet over here that's going to cause this velocity to get greater and greater? No, there's only one planet involved here. So if you neglect air resistance, and if there's no like rocket booster making this go faster in the x direction, it's just a ball being projected. So after that initial push, then what happens to the velocity in the x direction? Well, it's actually going to stay the same. So we drew 1, 2, 3 vectors here. I'm going to draw 3 vectors there. We'll start at the same exact position here. So we'll go 1, 2, 3, and try to make them as equal as possible, because the velocity isn't changing in the x direction. It's changing in the y direction because it's accelerating due to gravity. But in the x direction, if you neglect air resistance, there's no force that's causing this thing to accelerate in the x direction. Now, as soon as I introduce the word force, we're actually talking about dynamics. But all you have to know for now is that in the x direction, the velocity is constant. And that's why these vectors, 1, 2, 3, are all the same size. So now we have vectors in the x direction and we have vectors in the y direction. And just like before, we're going to add these vectors together on our nice diagram. And how do you add vectors? How do you add vectors? That's right, head to tail. So you can redraw this vector head to tail on this vector here, and you'd get something that looks like this. And then you could redraw your vertical vector if you wanted. This is like the parallelogram method there. And then you draw your resultant vector going from start to finish. So that's for the first part of our trajectory. Then you can continue doing this, and you're going to draw your vectors over here like this, and then you could draw your vertical vector from this position over here, and then you draw something like that. And then finally, you can draw your vectors going across this way. And I happen to run out of space here because I'm in a horizontal, I'm doing this on a video. But if you have a vertical, I'm in landscape. If you have a vertical like portrait page, you could do a fourth vector too, and you'll get even more of a projectile trajectory here. So as you can see, it's getting steeper and steeper and steeper. The path ends up looking parabolic. So it looks like this if you did like a infinitely large number of vectors within here, if you did the smaller and even smaller, then you would get a nice smooth projectile path. But we only did 3 points, but you could see that it's going to work out to be a nice parabola. Okay, so that's the path of a projectile. So some projectile vocabulary for you. Projectile motion is the curved path that an object follows when thrown, launched, or otherwise projected near the surface of Earth. It's important to note that we're not talking about a rocket ship that is being accelerated. That's a horrible rocket ship that would not go anywhere. But there's no force causing you to continue accelerating. It's just a ball that happened to be initially like kicked or thrown, and then it's like, okay, what happens to that path when you're near the Earth's surface or any other celestial body that has a gravitational pull? So trajectory is the path followed by an object in flight, and this path is parabolic for projectiles. If you don't have any of those other external forces, then besides gravity, then it's going to follow the path of a parabola. Range is the horizontal distance that the projectile travels, and that's a little bit weird if you're really into math. So this distance here, the horizontal distance, is known as the range. If you think of like a shooting range, or it's 100 meters down range. So they use range to show the x direction when we're talking about projectiles. And the reason I say that's different from math is because I know in the XY graphs, the range is the Y values, but that's not so when we're talking about projectiles because we use the vocabulary like, a shooting range. Hang time is the total amount of time that the projectile is in the air, similar to some of those free fall problems that we were doing before. So it's the total time. So we're going to be doing some of these problems, and it's very helpful to make what's called an X and Y T-chart. So we're going to write our given information in something that looks like this, and we'll have the D, VI, VF, A, and the T, the D, VI, VF, A, and the T. This is in the X, and this is in the Y. And when we actually do problems, we're going to fill this in, and then we could use our kinematic equations. Today's lesson, though, is just more conceptual, so it's not really necessary, but talking about conceptual, there are some things that we need to keep in mind while we fill in this chart. So the initial vertical velocity is 0 meters per second when we're talking about a horizontally fired projectile. Horizontally means all of the initial velocity is horizontal. So there's no component of this velocity that's pointing upward. You could have a projectile that looks like this, but we're just going to start with horizontal for now, and that means that the initial velocities in the y direction is always 0. And this is always going to be true as long as you're on the surface of Earth. The acceleration in the y direction is negative 9.8 meters per second squared. That's why our green vectors, when we drew the diagram, got longer and longer and longer. It's because you're accelerating downward. The horizontal velocity is constant. So if you look at these vectors, they're all the same size. So even as you're moving through your path, you're going to track along horizontally at the same rate. All right, and what does that mean for us for our XY chart? Well, if the initial velocity is equal to the final velocity, then let's say that this was 5 meters per second, it's going to stay at 5 meters per second over here. If this was 5, it's still going to be 5 over here, and the horizontal velocity when you hit the ground is still going to be 5. The vertical velocity is more, but the horizontal is 5. Why is that important? Well, what's the average velocity? V bar. 5 plus 5 divided by 2 is 5. So you don't need VIX and VFX. You can just write V bar X because it's the same. Okay? Unless you have a problem where they're telling you you're going to accelerate for some reason in the X direction, which isn't very common. Most of these, you're not accelerating in the X direction. And again, they'll tell you if you are, if this is like an honors question, then you can use V bar X, okay? And the horizontal acceleration, if it's a constant velocity, that means you're not accelerating. So actually, as you do more and more of these, since the acceleration's 0 all the time, you might not want to draw in this in your X, Y, T chart. And why is this good? Because we have a V bar, we have a D, and we have the T, and we can use the average velocity is equal to the displacement divided by the time on the X side of things. Every single time you could use this equation when you're talking about the X. For the Y side of things, you're accelerating, so you're going to have to use a different one of those kinematic equations. But this is basically what the XY chart is going to look like. It's a summary of all the concepts that you need to know. And that's about it. Thanks for watching, and have a great day.